So, for example, another example, if you take a look at x squared times sine x, again, notice you do have a polynomial function of x squared and a trig function, so you can do your tabular. So again, you're going to take the derivative of your x squared and take the derivative down till you get to a 0. Now remember your SC. Again, you're taking the derivative going down, you're integrating going up, and don't forget your two negative signs. So again, I'm going to integrate over and over again my second column. So your integral of sine x is going to be a negative cosine x. Your integral of a negative cosine is a negative sine x. The integral of negative sine x is a cosine x. And again, you want to draw your arrows, starting with a plus. So there's my plus. And then alternate your signs. Minus, plus. So multiply your products together. So I have x squared times negative cosine x. That's going to be negative x squared cosine x. Then I have 2x times a negative sine x. That's going to give me a positive 2x sine x. And then 2 times cosine x. And again, don't forget to add your c. So there is an example of tabular. Now when you take a look at c, cosine of square root of x, again, this is similar to a u substitution, because leaving that radical square root of x in there would make your tabular pretty messy. So what we're going to do is let's do a u sub. I'm going to call this t. So t is equal to the square root of x. Get rid of this square root so I can square t squared to give me just x. Because again, the idea is let's get rid of that radical, so that's why I'm going to square both sides. Now I'm going to take the derivative, so 2t dt is equal to dx. So now what I want to do is just rewrite this original integral in terms of t. So I have the integral of, again, I'm going to pull out this constant of 2, because what I need to do is replace this dx with this 2d dt. So I'm going to rewrite this pulling out the 2, t times the cosine of t dt. So and then we'll replace later, once we get done doing our integration, replacing our t's with the square root of x. So notice I can still do tabular because t is a polynomial function. So I'm going to take the derivative of t until it's down to a 0. So the derivative of t is just a 1, the derivative of 1 is 0. Integrate. Cosine of t. The integral of cosine is a sine t. The integral of sine is going to be a negative cosine. Again, do my tabular, draw your arrows, start with a plus and then a minus. So when I do my tabular, that's going to give me t times the sine of t. Now this is going to be 1 times a negative cosine t times a negative 1, so that's going to be plus cosine of t plus c. And don't forget, all of this is going to be multiplied by that constant of 2 that I pulled out of my integral. Now I'm going to replace my t's with the square root of x. So I end up with 2 times square root of x times the sine of square root x plus 2 times the cosine of square root x plus c. The idea was in the beginning was somehow to rewrite this integral without the square root. So again, if you have a definite integral, what you do, you still do your parts, you do the integration, and then like we've been doing, you have to plug your bounds in to evaluate. So for example, here's my definite integral going from 0 to 1 of inverse tangent of x dx. So again, my inverse trig, I'm going to let u be equal to the inverse tangent of x. My dv is just my dx. So the derivative of just inverse tangent, I know, is going to be 1 over 1 plus x squared dx. The integral of dx is just going to give me an x. So using my parts, I have u times v minus your integral v du. So I'm going to do my integration by parts. So u times v, so that's going to be x times your inverse tangent of x, minus your integral of v, which is x, times my du, which is 1 over 1 plus x squared dx. So I have x times your inverse tangent of x minus your integral of x over 1 plus x squared dx. So I'm going to have to do a u sub to integrate this. So u is going to be equal to 1 plus x squared. My du is going to be 2x dx. Remember, x inverse tangent of x is he's tagging along. Minus, remember, because I've got 2x dx, so there's the x dx, I have to divide out a 1/2. And I can rewrite my integral as 1 over u du. So now when I integrate, again, there's my x inverse tangent of x minus 1/2 times the natural log. Again, I'm going to replace the 1 plus x squared for u. And again, this is a definite integral. My bounds are going from 0 to 1, so I don't write that plus c. So just like using the fundamental theorem of calculus, I plug the upper bound in minus the lower bound. So I have 1 times your inverse tangent of 1 minus 1/2 times the natural log of 2. 1 plus 1 is 2. Minus. Now be careful, you've got trig and you've got log, so be sure, don't just disregard this as a 0. 0 times inverse tan is 0, that is a 0. Minus 1/2 times the natural log of 1. Well, natural log of 1 is 0, so again, my lower bound will just be a minus 0. Evaluate that inverse trig. Inverse tangent of 1 is pi over 4 minus 1/2 times the natural log of 2. So you do all your parts, you integrate, then you plug in your upper and your lower bound. So now when you take a look at x plus x times the cosine of x, remember, using your rules of integration, I can split this up going from 0 to pi of x dx plus 0 to pi of x cosine of x dx. So again, I can integrate x dx as just an x squared over 2. And again, I can evaluate this from 0 to pi. So that's going to give me pi squared over 2 plus something. So now let me worry about integrating by parts this x times cosine of x. You can do tabular because x is a polynomial function. Or you can do parts. So again, take the derivative of x down to a 0. Derivative of x is 1, derivative of 1 is a 0. Integrate cosine of x. The integral of cosine x is a sine x. Integral sine x is a negative cosine x. Draw your arrows starting with the plus sign and then alternate with a negative. So again, I have x times sine x. I have 1 times a negative negative cosine x, which is going to give me a plus cosine x. Again, I've already evaluated the pi squared over 2, so I need to find my bounds of 0 to 1 for the x sine x plus cosine x. So pi squared over 2 just tags along for my answer. Plug in my 1. Oh, excuse me, it's a pi, not a 1. So plug in my pi. So I end up with pi times the sine of pi plus cosine of pi minus, plug in your lower bound. Well, I know 0 times anything 0 plus cosine 0. So when I evaluate this, I end up with pi squared over 2. Sine of pi I know is 0. Cosine of pi is a negative 1. Minus cosine of 0 is 1. So I end up with pi squared over 2 minus 2. So that's how when you have to use integration by parts with a definite integral.